Okay, so what I'm going to do is I'm going to try to give you a little bit of a start on each of these problems or some examples to review. But I'd really like for you to attempt the problems, and if you have further questions, you can email me again. So for 15, let's read it real quick. It says, biologists have noticed that the chirping rate of crickets of a certain species is related to the temperature, and the relationship appears to be very nearly linear. So that's our first really important thing. We're going to model this as a line. That's what they're saying. Now next, they're going to give us a series of data points. The crickets produce 113 chirps per minute at the temperature 70 degrees Fahrenheit, 173 chirps per minute at a temperature of 80 degrees Fahrenheit. Those are 2 points in our data. Since it's a line, we should be able to construct a line using those 2 data points. Questions A, B, and C are trying to guide you through that process. What you need to be asking yourself is, what is my independent and dependent variable? If I'm going to make a graph, what should go on the horizontal axis and what should go on the vertical axis? Now, the data they gave us, one was number of chirps, and the other one was temp, the temperature. So reading this very carefully, find a linear equation that models the temperature as a function of the number of chirps per minute. That's going to help us determine which variable should go on which axis. And then from there, we can plot the data, the 2 data points that they gave us, form the line, and answer the other questions. So that should help you get started on that question. Now for 41 through 46, this is compositions of functions. And really all they're asking is they've already done the composition of functions and they want you to express each thing as a composition of function. So let me give you an example. Let's say that I have the function sine of x to the third, which is also sometimes written as sine to the third x. This is a composition of functions, and what they want me to do is to write it as if it was a function of another function of x, which is also sometimes written f of g of x up there like that. In this case, my inner function is, my g of x is sine here. So here, g of x is equal to sine x, and my outside function is the power. So f of x is equal to x to the third. When I plug in sine of x, which is my f of x, or my g of x, into x for f of x, that's how a composition of functions works. That's when it becomes
Jim Bender! Hey, I need you up here at the lobby, please.
Sine x to the third. Okay, so there's a quick review of composition of functions, and that's all they want you to do. They want you to take these functions and split them apart into f and g. So what's the outside function and what's the inside function? Okay. All right, for 55, it says a ship is moving at a speed of 30 kilometers per hour parallel to a straight shoreline. The ship is 6 kilometers from the shore and it passes a lighthouse at noon. So this first statement here is just like that last question that you asked the other day. This is something you're going to have to take some time to draw a diagram for. So I'd like to see you do that. Draw a picture of a shore, a ship that's 6 kilometers away from the shore. Label that it's traveling 30 kilometers per hour straight, parallel to the shoreline, and that it passes a lighthouse at noon. So at noon, it should be right next to the lighthouse. Now, once you draw that picture, that's going to help you imagine what's going on in the next question. So it says express the distance s between the lighthouse and the ship as a function of d. So what you should do is, once you've drawn that first diagram, remember the ship is moving straight, parallel to the shoreline. So draw a second diagram and have the ship be somewhere farther along the shoreline, away from now the lighthouse, and try to imagine a line between the lighthouse and where the ship is sometime afternoon. If you draw those two pictures, you're going to see that there's a simple relationship that will help you determine the distance between the lighthouse and the ship. Keep in mind that the lighthouse is going to be on the shore. Okay, so let's move on to the next one. This one's going to be a little bit different. We need to manipulate it. So the first step would be to, if we've got a problem and we're not really sure what to do, the first step is usually to try to re-express it, write it in a different way than the book presented it. So we'll try this. This is equivalent to what the book wrote. We just wrote the reciprocal instead of having a negative exponent. From there, if we look at the examples in the book, none of them really show us any rules that would allow us to get rid of the e to the x. Normally, we're going to be using an inverse function by saying, well, the inverse function of e to the x is natural log. And if we do that composition, it'll be equal to x. So we usually use that property to help us solve these kinds of problems. The difficulty here is that we can't get those e to the x terms together, and there isn't a property that we can use for something like this. So that's making it very difficult for us. So we're going to need to continue to try to re-express it. One idea would be to multiply both sides by e to the x, so that we don't change the value of the equation. So this is going to be e to the x squared plus 1 equals 3e to the x. Then we've got, if we keep rewriting it, we've got e to the x squared minus 3e to the x plus 1 equals 0. If we think of this as if it was x squared minus 3x plus 1, that looks like a quadratic, and we could solve it using the quadratic equation. And in fact, that's the same way that we're going to solve this problem, is by thinking of it as a quadratic. You're going to use the quadratic equation, and you're going to get x equals some number. But in this case, it's not x that equals that number, it's e to the x. Okay? All right, now 41 is an application of using the inverse formula for the natural log, which is e to the x. Now, you want to be really careful with the summer packet. Before you're attempting the homework, you do need to read carefully through the examples and maybe try some of the examples out. You'll notice that example 4 in the summer packet is actually identical to this question. So you might want to take a closer look at example 4 and let me know if you have any questions after you've gone over these problems one more time.